2.5 million light-years away, a galaxy containing 1 trillion stars is hurtling toward us at 250,000 miles per hour. For decades, we thought we understood Andromeda. We measured it, mapped it, cataloged its light. We were confident in our assessment of its size, its mass, its nature. Then the James Webb Space Telescope turned its infrared eyes toward our nearest galactic neighbor, and everything changed. The galaxy we thought we knew revealed itself to be something far more vast, far more complex, and far more connected to our own fate than anyone had imagined. The numbers alone should make you pause. Andromeda spans 220,000 light-years in diameter, making it more than twice the width of our Milky Way. Its trillion stars outmass our galaxy's 400 billion by a factor of 2.5. But these statistics, impressive as they sound, told only a fraction of the story. What JWST discovered in 2023 and 2024 wasn't just a refinement of measurements. It was a fundamental recalibration of our understanding of galactic architecture, stellar evolution, and the very nature of cosmic structures. Before Webb, our view of Andromeda came primarily from visible light observations. Hubble gave us stunning images of its spiral arms, its dust lanes, its bright stellar nurseries. Ground-based telescopes mapped its rotation, its chemical composition, its distance. We built sophisticated models of its formation history, its current dynamics, its future trajectory. Every astronomer could tell you Andromeda's basic statistics, yet we were observing only a narrow slice of reality, like trying to understand an orchestra by listening to a single instrument. Infrared vision changes everything. Light that took 2.5 million years to reach us, light that passed through cosmic dust and gas that would have blocked visible wavelengths, suddenly became accessible. JWST's instruments penetrated barriers that had hidden entire populations of stars, revealed structures invisible to every previous telescope, and exposed processes that reshape our understanding of how galaxies grow, evolve, and interact. What emerged from these observations wasn't the Andromeda of textbooks. It was something stranger, more dynamic, and more intimately connected to the cosmic web than our models had predicted. The first hint came from unexpected infrared signatures in Andromeda's outer halo. Scientists analyzing JWST data noticed emission patterns that shouldn't exist according to standard galactic models. Further investigation revealed vast streams of ancient stars, evidence of cannibalized dwarf galaxies, extending far beyond what anyone had mapped before. The galaxy's true boundary, it turned out, reached nearly twice as far as previous estimates suggested. Andromeda wasn't just bigger in terms of raw diameter, it was fundamentally more extensive, more gravitationally influential, and more structurally complex. But size represents only the beginning of Webb's revelations, the telescope's ability to resolve individual stars in Andromeda's core regions provided unprecedented insight into stellar populations. Astronomers could suddenly distinguish between stars formed in different epochs, trace the chemical evolution of the galaxy across billions of years, and identify structures that revealed Andromeda's violent past. Every observation added layers to a story that grew richer and more intricate. The galaxy became less like a static object and more like a living archive of cosmic history. Dr. Julian Dal Canton, one of the leading researchers studying JWST's Andromeda observations, noted in late 2024 that the telescope had delivered more detailed information about our neighboring galaxy in 18 months than ground-based facilities had provided in 50 years. The resolution, the wavelength coverage, the sensitivity all combined to create what she called a dimensional shift in galactic astronomy. Questions that had remained theoretical for generations suddenly became answerable. Mysteries that seemed permanently out of reach moved within the domain of empirical investigation. Tonight, you're going to discover what JWST revealed about the true scale of Andromeda, not just its physical dimensions, though those are staggering enough. We're exploring the scale of its influence, the scale of its history, the scale of its future impact on everything we call home. You'll learn why our previous understanding was incomplete, how infrared observations changed the entire picture, and what these discoveries mean for our place in the universe. By the time we finish this journey, You'll never look at that faint smudge in the autumn sky the same way again. If you are fascinated by the frontiers of space exploration and the profound discoveries reshaping our cosmic perspective, subscribe and hit the thumbs up button. And here is a question worth contemplating: if Andromeda is so much larger and more complex than we realized, what else in the universe have we fundamentally misunderstood? Comment below with your thoughts. I'll pin the most thought-provoking answer. 3 revelations structure our exploration tonight. First, the physical scale revelation, where JWST's observations expanded Andromeda's known boundaries and exposed structures invisible to previous instruments. Second, the temporal scale revelation, where the telescope's ability to resolve ancient stellar populations revealed billions of years of galactic history written in starlight. Third, the existential scale revelation, where understanding Andromeda's true nature forces us to reconsider our galaxy's fate and humanity's cosmic context. The story begins not with the latest technology but with the oldest light, with photons that departed Andromeda when our Australopithecine ancestors walked the African savanna. Those photons carried information encoded in wavelengths our eyes cannot see, waiting to 0.5 million years for an instrument sophisticated enough to decode their message. That instrument arrived at the second Lagrange point in 2022. Now let us begin with what it found. Galactic Foundation. Andromeda occupies a unique position in human cosmic awareness. Unlike distant galaxies reduced to mathematical abstractions, and like our own Milky Way whose structure we infer from interior observations, Andromeda presents itself as a complete galactic system visible in its entirety. We see it face on, tilted just enough to reveal its structure, close enough for detailed study yet far enough for comprehensive perspective. This geometry makes Andromeda the perfect laboratory for understanding galactic architecture. Every insight gained from studying our neighbor illuminates galactic physics everywhere. The galaxy first entered scientific consciousness in 964 CE when Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud in his Book of Fixed Stars. For nearly a millennium afterward, observers noted its existence without understanding its nature. Was it a nebula within our stellar system? A cloud of luminous gas? The question remained unanswered until 1925, when Edwin Hubble's observations of Cepheid variable stars in Andromeda proved it lay far beyond the boundaries of the Milky Way. That discovery expanded the known universe overnight. What seemed like a modest patch of cosmic fog revealed itself as an entire galaxy of hundreds of billions of stars, an island universe comparable to our own. Early measurements relied on visible light, the same wavelengths our eyes perceive. Astronomers photographed Andromeda through progressively larger telescopes, mapping its spiral structure, identifying its brightest stars, measuring its rotation velocity. By the 1950s, the basic statistics were established. Distance, approximately to 0.5 million light-years. Diameter, roughly 220,000 light-years. Mass, around 1 trillion solar masses. These numbers entered textbooks and remained relatively stable for decades. Refinements occurred, precision improved, but the fundamental picture stayed consistent. Then came the realization that visible light tells an incomplete story. Dust pervades galaxies, microscopic particles of carbon, silicon, and various ices formed in stellar atmospheres and supernova explosions. This dust absorbs and scatters blue and visible wavelengths while allowing longer infrared wavelengths to pass through relatively unimpeded. Observing Andromeda in visible light meant seeing only the dust-free regions, the areas where starlight could escape unobscured. Entire populations of stars, whole structural components, remain hidden behind cosmic soot. Infrared astronomy developed slowly because Earth's atmosphere radiates strongly at these wavelengths, overwhelming faint cosmic signals. Early infrared telescopes operated from mountaintops and high-altitude aircraft, grabbing brief glimpses through atmospheric windows. The Spitzer Space Telescope, launched in 2003, provided the first comprehensive infrared survey of Andromeda, revealing vast amounts of cold dust and previously unknown stellar populations. Those observations hinted at complexity beyond visible light appearances, but Spitzer's mirror measured just 85 centimeters across. Its resolution could map large-scale structures but couldn't resolve individual stars or fine details. JWST changed the game entirely. Its 6.5-meter primary mirror collects nearly 60 times more light than Spitzer. Its instruments operate at wavelengths from 0.6 to 28 microns, spanning near-infrared through mid-infrared. Its location at the second Lagrange point, 1.5 million kilometers from Earth, places it in permanent shadow where passive cooling brings instruments to operating temperatures below 50 Kelvin. This combination of size, wavelength coverage, and sensitivity created an observational capability without precedent. The telescope's first observations of Andromeda began in early 2023 as part of a program led by teams from the University of Washington and the Space Telescope Science Institute. The initial target was Andromeda's northeast spiral arm, a region where Hubble observations had identified active star formation. JWST's near-infrared camera captured images revealing individual red giant stars, dust-enshrouded protostars, and complex filamentary structures invisible in optical wavelengths. The detail was extraordinary. Features that appeared as indistinct blobs in Hubble images resolved into clusters of distinct objects, each with measurable brightness and color. But the real surprises emerged when astronomers pointed JWST at Andromeda's outer regions, the diffuse halo extending far beyond the bright spiral disk. Previous observations had detected some stars in these areas, but the exact extent and structure of the halo remained uncertain. Infrared observations revealed streams of stars following coherent orbital paths, evidence of smaller galaxies that Andromeda had consumed and dismembered. These tidal streams traced out volumes far larger than the visible galaxy, extending Andromeda's gravitational influence across a sphere nearly 500,000 light-years in diameter. To put this in perspective, the expansion doubled Andromeda's known extent. The galaxy wasn't just 220,000 light-years across. Its stellar halo, its gravitational sphere of influence, its total structural system reached more than twice that distance. This wasn't a minor refinement. It represented a fundamental reframing of what constitutes a galaxy. The bright spiral disk visible in optical images forms only the core of a far more extensive system, like an iceberg whose bulk remains submerged beneath perception. This discovery immediately raised questions about our own galaxy. If Andromeda's true extent reaches twice its visible diameter, presumably the Milky Way possesses similar extended structures. Recent surveys have indeed identified vast stellar streams in our galactic halo, remnants of cannibalized dwarf galaxies. The two galaxies, already recognized as the dominant members of the local group, revealed themselves as even more massive and gravitationally influential than previous models suggested. Their interaction, their inevitable collision, suddenly took on new dimensions of complexity. The foundational understanding established by these observations sets the stage for everything that follows. Andromeda isn't simply large by human standards. It represents a gravitationally bound system of 1 trillion stars, vast quantities of gas and dust, and dark matter outweighing all visible components by a factor of 10. This system has existed for over 10 billion years, growing through mergers and accretion, forming stars in bursts and lulls, evolving through processes that JWST's observations are only now beginning to illuminate. Every subsequent revelation builds on this foundation. Andromeda is vastly more extensive, more complex, and more dynamic than decades of visible light observations could reveal. Consider what this means for observation. When you look at Andromeda with your naked eye from a dark site, you see a faint oval smudge. That smudge contains 1 trillion stars. But even that incomprehensible number understates reality. The stars you see, or rather the collective glow you perceive, represent only the brightest fraction of Andromeda's stellar population. The red dwarfs, the brown dwarfs, the ancient remnants that dominate by sheer numbers remain invisible, their faint light overwhelmed by brighter siblings. JWST's infrared vision penetrates this bias, revealing stellar populations that constitute the bulk of galactic mass but contribute little to visible appearance. The galaxy's structure follows patterns both familiar and strange. Spiral arms wind outward from a central bar, regions where density waves compress gas and trigger star formation. A massive bulge dominates the center, a roughly spherical concentration of ancient stars formed when the galaxy was young. Globular clusters orbit in the halo, gravitationally bound spheres each containing hundreds of thousands of ancient stars. Dark matter pervades the entire structure, providing gravitational scaffolding that holds everything together despite the system's enormous size. Yet this description, accurate as far as it goes, fails to capture the dynamic reality. Andromeda isn't a static configuration. Stars orbit the galactic center at speeds approaching 250 kilometers per second. Gas clouds collide and form new generations of stars. Supernovae explode and enrich the interstellar medium with heavy elements. Black holes lurk in stellar remnants and in the galactic core. The entire system rotates, evolves, and interacts with its environment. What we see represents a single moment in a 10 billion year history, a photograph of a process still unfolding. Understanding this foundation matters because it contextualizes every discovery that follows. When JWST reveals unexpected stellar populations, we interpret them against our knowledge of galactic structure. When infrared observations expose hidden dust lanes, we understand their role in star formation and chemical evolution. When measurements extend Andromeda's boundaries, we grasp the implications for galactic dynamics and cosmic evolution. The foundation isn't merely preliminary information. It's the framework that makes deeper insights possible. What JWST established in its first 18 months of Andromeda observations was both confirmation and revolution. Confirmation that our basic understanding of galactic structure holds true when tested at unprecedented precision. Revolution in the details, the extent, the complexity of processes that become visible when observational barriers fall away. The galaxy revealed itself as more vast and more intricate than anyone anticipated, yet still comprehensible within the physics we've developed to understand such systems. This sets up our next exploration. Now that we understand Andromeda's basic architecture and the expansion of its known boundaries, we need to examine what exists in those newly revealed regions. What populations of stars and structures JWST discovered in areas previously hidden from view. And what those discoveries tell us about how galaxies grow and evolve across cosmic time. Hidden populations, the stars we see with our eyes, tell a biased story. Hot, massive, luminous stars dominate visible light observations despite their relative rarity. These stellar giants shine thousands or millions of times brighter than the sun, but they're evolutionary sprinters, burning through their nuclear fuel in millions rather than billions of years. By contrast, the cool red dwarfs that constitute perhaps 75% of all stars contribute little to a galaxy's visible light. They're faint, long-lived, and easily overlooked. Understanding Andromeda's true stellar census requires seeing these overlooked populations, and that demands infrared observation. JWST's first comprehensive survey of Andromeda's stellar populations targeted regions where dust extinction made optical observation impossible. One particularly revealing study focused on a dust lane along the galaxy's inner spiral arm, a feature visible in Hubble images as a dark ribbon where starlight couldn't penetrate. Pointing JWST's near-infrared camera at this apparently empty region revealed it as anything but void. Thousands of red giant stars emerged from invisibility, their cool surfaces radiating primarily in infrared wavelengths. These stars, evolved descendants of sun-like progenitors, traced out structures that optical astronomers had been forced to infer rather than observe. The revelation went beyond simple detection. By measuring the brightness and color of individual stars in infrared wavelengths, astronomers could determine their ages, chemical compositions, and evolutionary states. This created what researchers call a color magnitude diagram, a fundamental tool in stellar astrophysics. Plot a population of stars by their color and brightness, and patterns emerge that reveal when they formed, what materials they contained at birth, and where they sit on the evolutionary track. From main sequence through giant phase to final remnant. JWST's resolution allowed such diagrams to be constructed for Andromeda's stellar populations with unprecedented detail. What emerged surprised researchers familiar with our own galaxy. Andromeda's stellar populations showed evidence of a complex formation history, multiple bursts of star formation separated by quiescent periods. The distribution of stellar ages didn't follow a smooth progression. Instead, distinct generations appeared, each chemically enriched compared to its predecessors. This suggested that Andromeda's growth hadn't been gradual and steady. The galaxy experienced episodes of intense activity, likely triggered by mergers with smaller systems that brought fresh gas to fuel star formation. Evidence for this violent past appeared throughout JWST's observations. The stellar streams in Andromeda's outer halo, mentioned earlier, represent the clearest signatures of galactic cannibalism. When a small dwarf galaxy falls into a larger system, tidal forces stretch it into elongated streams. The stars from the devoured galaxy maintain their orbital coherence for billions of years, tracing out the path of their parents' demise. JWST's ability to detect faint red giants in these streams allowed astronomers to map them with extraordinary precision, revealing at least 5 distinct streams, each representing a separate merger event. One particularly prominent stream, designated the Giant Southern Stream, extends across 150,000 light-years of Andromeda's halo, discovered initially through wide-field surveys. This structure gained no clarity in JWST observations. Individual red giants could be identified and measured, their properties compared with stars in Andromeda's main body and with surviving dwarf galaxies orbiting nearby. The analysis revealed that the Giant Southern Stream originated from a dwarf galaxy with perhaps 100 million stars that Andromeda consumed roughly 2 billion years ago. The merger added mass to Andromeda but also disrupted the outer regions of the galaxy, triggering waves of star formation that propagated through the disk. Similar merger signatures appeared in Andromeda's central regions. JWST observations of the galactic core, where optical observations struggled due to extreme crowding and dust extinction, revealed complex stellar populations that couldn't form through isolated evolution. Young stars appeared in regions dominated by ancient populations, suggesting that gas brought in through mergers had fallen to the center and formed new stellar generations even in this evolved system. The central supermassive black hole, weighing approximately 100 million solar masses, showed evidence of recent feeding, possibly triggered by the same merger events that brought fresh gas to the core. These discoveries reshaped understanding of galactic evolution. Previous models treated galaxy growth as primarily smooth, with gas gradually accreting from the cosmic web and forming stars at a relatively steady rate. Mergers were recognized as important but treated as disruptive events rather than fundamental drivers of evolution. JWST's observations of Andromeda suggested a different picture. Mergers appeared to be central to galactic development, bringing not just mass but also fresh gas that rejuvenates star formation, triggers nuclear activity, and maintains galactic vitality across billions of years. The revelation extends to understanding our own galaxy's future. The Milky Way is currently consuming the Sagittarius dwarf elliptical galaxy, a process that JWST observations of Andromeda help contextualize. The tidal streams stretching from the Sagittarius dwarf through our galactic disk represent the same phenomenon visible in Andromeda's halo. Our galaxy has grown through similar cannibalism, and it will experience an even more dramatic merger when Andromeda itself arrives in approximately 4 billion years. Understanding Andromeda's merger history provides a preview of our own galactic future. But stellar populations represent only part of the hidden story. JWST's mid-infrared observations revealed vast quantities of cool dust distributed throughout Andromeda's disk and halo. This dust, composed primarily of silicate and carbon grains formed in stellar atmospheres, serves as the raw material for future star formation. Its distribution traces out the galaxy's recent history of stellar mass loss and supernova explosions. Regions with enhanced dust concentrations mark areas where massive stars formed, evolved, and died, enriching their surroundings with heavy elements. The total dust mass in Andromeda, calculated from JWST observations, reaches approximately 100 million solar masses. This represents a small fraction of the galaxy's total mass but plays a crucial role in galactic ecology. Dust grains shield forming stars from disruptive radiation, facilitate the cooling of gas clouds that allows them to collapse, and catalyze the formation of molecular hydrogen that fuels star formation. Without dust, galaxies would look entirely different, their star formation rates suppressed, their ability to evolve compromised. JWST also detected organic molecules in Andromeda's interstellar medium, complex carbon-based compounds formed through chemistry occurring on dust-grained surfaces. These molecules, including polycyclic aromatic hydrocarbons, represent some of the most complex chemistry occurring naturally in space. Their presence throughout Andromeda's disk suggests that the chemical precursors of life aren't unique to our solar system or even our galaxy. The same processes that generated the organic molecules in the clouds from which Earth formed operate throughout Andromeda's trillion star system. Consider the implications. Each of those trillion stars represents a potential site for planet formation. If even a tiny fraction develop planetary systems, Andromeda contains billions of worlds. Some fraction of those worlds will orbit in their star's habitable zones, regions where liquid water can exist on planetary surfaces. The organic molecules JWST detected, combined with water ice that surely exists throughout the galaxy, provide the chemical foundation for biochemistry. Life, if it arose at all in Andromeda, likely arose billions of times, on billions of worlds, across 10 billion years of galactic history. Yet we see none of it. No radio signals, no signs of astroengineering, no evidence of galaxy-spanning civilizations despite countless opportunities for such to rise. This absence, this cosmic silence, poses questions that JWST observations make more pressing. Either life is vanishingly rare despite favorable conditions, or something prevents it from developing to detectable scales, or detection requires methods we haven't yet conceived. Andromeda, in its vastness and its silence, embodies the Fermi paradox at galactic scale. The hidden populations that JWST revealed aren't just scientific curiosities. They represent the bulk of Andromeda's stellar mass, the majority of its stars, the cumulative result of 10 billion years of galactic evolution. Previous observations captured the most visible stars, the brightest objects, the most obvious features. Infrared vision penetrated those biases to reveal reality in fuller dimension. The galaxy that emerged was older, more complex, more thoroughly shaped by mergers and accretion than optical observations suggested. This realization forces a reconsideration of galactic astronomy more broadly. How many other galaxies hide similar complexity behind dust obscuration and observational bias? What populations remain undiscovered in distant systems where even JWST's remarkable capabilities cannot resolve individual stars? The answer suggests that our census of the universe remains incomplete, that structures and processes we haven't yet detected may rival or exceed those we have cataloged. For Andromeda specifically, understanding these hidden populations transforms our view of the galaxy from a static structure into a dynamic system shaped by specific events across its history. The stars JWST revealed didn't form uniformly and gradually. They emerged in bursts triggered by mergers, clustered in regions where gas concentrations allowed star formation, and spread through the galactic volume as the system evolved. Every population carries information about the conditions of its birth, information written in chemical abundances and spatial distributions that JWST's observations can decode. What becomes clear is that scale extends beyond mere physical size. Andromeda's true scale encompasses temporal dimension, the billions of years of history archived in stellar populations, and the complexity scale, the intricate processes that shaped its current configuration. Understanding these scales requires seeing the hidden, detecting the overlooked, and recognizing that the obvious represents only a fraction of reality. Spiral architecture. Spiral galaxies rank among the universe's most visually striking structures. Arms of bright stars and glowing gas wind outward from central hubs in patterns that seem almost artificial in their regularity. Yet these spirals aren't permanent features. They're density waves, transient compressions in the galactic disk that propagate through the stellar population like ripples on a pond. Individual stars drift in and out of their arms as they orbit, spending most of their lives in the interarm regions. The spiral pattern persists while its constituent parts change, creating an illusion of solidity from dynamic flow. Understanding spiral structure has challenged astrophysicists since the nature of galaxies became clear in the 1920s. If the spiral arms were material features rotating with the stars, differential rotation would wind them tighter with each galactic orbit. After a billion years, their arms should have wrapped dozens of times around the galactic center, creating a tight whirl that doesn't match observations. This winding problem led to the density wave theory developed in the 1960s by Lin and Xu, which treats spiral arms as waves propagating through the disk rather than fixed structures. JWST observations of Andromeda provided the most detailed test yet of spiral structure theory. The telescope's resolution allowed individual star-forming regions to be traced along spiral arms, their ages determined from infrared colors and luminosities. What emerged confirmed the basic density wave picture while revealing complications that simpler models hadn't predicted. The spiral pattern does indeed represent a density wave, but that wave is neither uniform nor stable. It varies in strength along its length, fragments in some regions, and shows evidence of perturbations from the galaxy's complex merger history. One of JWST's most revealing observations targeted a section of Andromeda's outer spiral arm, where optical images suggested active star formation. The near-infrared camera captured a region approximately 5,000 light-years across in extraordinary detail. Dozens of star-forming clouds appeared, their infrared emission revealing protostars still embedded in the gas and dust from which they're condensing. The arrangement wasn't random. The star-forming regions aligned along the spiral arm's inner edge, exactly where density wave theory predicts gas compression should be strongest. But the observation revealed something unexpected. Not all star-forming regions showed the same age. Some contained stars barely 1,000,000 years old, still surrounded by natal material. Others hosted stars 10 million years old, already emerged from their birth clouds. The age gradient suggested that star formation doesn't occur simultaneously along the entire spiral arm. Instead, it propagates, with one generation of star formation triggering the next through supernova shockwaves or radiation pressure compressing nearby clouds. This sequential star formation creates structure within structure, nested patterns where the large-scale spiral wave sets the stage for more complex local dynamics. The spiral arms themselves showed variations that challenged simplified models. Andromeda possesses two major spiral arms, as expected for a galaxy with a strong central bar like the one JWST observations confirmed in the galactic core. But additional arm segments appeared between the major spirals, partial structures that didn't extend all the way around the galaxy. These features, termed spurs or feathers, branch off from the main arms at specific locations. Their presence suggests that Andromeda's spiral structure results not from a single, coherent density wave but from multiple overlapping waves with different pattern speeds and orientations. Tracing the spiral pattern into Andromeda's outer regions revealed progressive weakening. The arms grow fainter and more fragmented at large radii, eventually dissolving into the diffuse outer disk. This matches theoretical expectations. Density waves lose coherence as they propagate into regions where the stellar disk thins and self-gravity weakens. But JWST detected structures even in these outer regions, partial spirals and arcs that suggested density perturbations propagating through the sparse outer disk. These features, invisible in optical observations, hinted at complexity extending to the edges of Andromeda's visible structure. The central bar, visible in JWST's near-infrared images with unprecedented clarity, plays a crucial role in driving and maintaining the spiral pattern. Bars form naturally in disk galaxies through instabilities in the stellar distribution. Once formed, they funnel gas toward the galactic center while launching density waves that propagate outward as spiral arms. Andromeda's bar measures approximately 25,000 light-years in length, a substantial structure oriented roughly perpendicular to our line of sight. Its presence explains why Andromeda exhibits a two-armed spiral pattern rather than the more fragmented multiple-arm structure seen in some galaxies. JWST observations also captured the bar's influence on Andromeda's central regions. Gas streaming along the bar feeds star formation in a ring around the galactic nucleus, a feature already known from optical observations but revealed in new detail in infrared wavelengths. This nuclear ring contains dozens of massive star-forming complexes, each forming stars at rates exceeding anything found in the solar neighborhood. The ring's existence demonstrates how bars channel gas inward, concentrating fuel for star formation in the central kiloparsec. Without the bar, Andromeda's core would look entirely different, its star formation quenched by lack of fresh gas. Comparing Andromeda's spiral structure to the Milky Way's reveals both similarities and differences. Our galaxy also possesses a central bar and spiral arms, though seeing our structure from inside makes determining exact patterns difficult. We infer the Milky Way's structure through indirect methods, mapping spiral arms by locating star-forming regions and tracing gas distributions. Andromeda provides the outside view we can never achieve for our own galaxy, allowing astronomers to study galactic structure with complete perspective. What we learn from Andromeda informs models of the Milky Way, providing context for our partial, anterior view. The dust lanes visible in optical images of Andromeda, dark ribbons tracing the inner edges of spiral arms, appear transformed in JWST infrared observations. Rather than voids, these dust lanes revealed themselves as sites of intense activity. Cool dust glowed in mid-infrared wavelengths, marking regions where massive stars had recently formed and begun enriching their surroundings with heavy elements. Embedded protostars appeared throughout the dust lanes, stars still gaining mass from their surrounding envelopes. These observations confirmed that dust lanes mark the spiral arm regions where gas compression initiates star formation, exactly as theory predicts. One particularly striking JWST image captured a region where two spiral arms appeared to interact. The overlapping density waves created a zone of enhanced compression where star formation proceeded at elevated rates. Dozens of massive star clusters appeared in this intersection region, gravitationally bound groups of thousands to tens of thousands of stars all born from the same gas cloud. These clusters, detected in infrared but obscured in optical wavelengths by surrounding dust, represent some of the most intense star-forming environments in the local universe. Given enough time, they'll evolve into globular clusters like those orbiting in Andromeda's halo, ancient remnants that outlive their birth environments by billions of years. The physical scale of Andromeda's spiral structure staggers comprehension. A single spiral arm spans 100,000 light-years or more from the galactic center to its dissolution in the outer disk. At Andromeda's rotation velocity of roughly 250 kilometers per second, a star near the Sun's equivalent radius completes one galactic orbit in approximately 250 million years. The spiral pattern, rotating more slowly than the stars, creates a context through which stellar populations flow, spending perhaps 10 to 20 million years transiting each arm crossing. During that relatively brief passage, the increased density triggers cloud collapse and star formation, generating the bright, young stellar populations that define the spiral arm's invisible light. This temporal dimension adds crucial perspective. When we observe Andromeda's spirals, we're not seeing fixed structures. We're witnessing a snapshot of patterns that will look different in 10 million years and entirely transformed in a billion. The specific star-forming regions JWST captured in such detail represent transient features, their constituent stars soon to disperse into the general stellar population. The density wave will persist, but it will be traced by different stars, newly formed in clouds that haven't yet collapsed. Andromeda's spiral pattern represents dynamic equilibrium, structurizing from flow rather than permanent configuration. Understanding this architecture matters for grasping galactic ecology. Spiral arms aren't mere aesthetic features. They're fundamental to how galaxies process gas into stars, how metals spread through galactic disks, how stellar populations mix and evolve. Without spiral structure, star formation would proceed more slowly and uniformly, perhaps gradually to build the stellar masses we observe. The density wave mechanism concentrates star formation in space and time, creating efficiencies that simpler models based on gradual gas accretion cannot achieve. For observers attempting to understand Andromeda's true scale, spiral structure provides a measuring stick written in light. The spacing between arms, their strength and coherence, their rate of star formation all encode information about the galaxy's mass distribution, rotation curve, and dynamical state. JWST's detailed observations allow these parameters to be measured with unprecedented precision, refining models of Andromeda's mass, composition, and evolution. Each measurement adds constraint to our understanding, reducing uncertainty and revealing the galaxy in higher fidelity. What emerges is a picture of Andromeda as a coherent system despite its vast scale. The spiral structure connects core to outer regions, channeling material and organizing star formation across 200,000 light-years of galactic real estate. This coherence, this integration, demonstrates that galaxies aren't merely collections of stars but organized systems shaped by gravity, rotation, and wave dynamics. Understanding their architecture reveals principles that apply throughout the universe. Wherever disk galaxies form and evolve. Temporal depth. Every star carries within its spectrum a chemical history written in absorption lines. The hydrogen and helium that constitute most stellar mass came from the Big Bang, primordial elements created in the universe's first minutes. But the heavier elements, everything from carbon to uranium, formed through nuclear fusion in stellar cores and supernova explosions. Generations of stars must live and die to build up substantial quantities of these metals, as astronomers term all elements heavier than helium. Measuring stellar metallicities allows astronomers to determine when stars formed in galactic history, earlier generations being metal-poor while later stars inherit enriched material. JWST's spectroscopic capabilities enabled metallicity measurements for individual stars in Andromeda's halo with unprecedented precision. The near-infrared spectrograph captured the light from red giant stars, spreading it into spectra where absorption lines from calcium, magnesium, iron, and other elements could be measured. Comparing the strengths of these lines to hydrogen revealed each star's iron-to-hydrogen ratio, typically written as Ph in logarithmic notation. The measurements revealed an extraordinary range, from stars with 1/100th the sun's metal content to others approaching twice solar metallicity. This range encodes 10 billion years of chemical evolution. The most metal-poor stars formed when Andromeda was young, perhaps within the first billion years after the Big Bang. At that epoch, only a few generations of stars had lived and died, so the interstellar medium contained relatively little enriched material. Stars forming from that pristine gas inherited low metallicities that they preserved throughout their multi-billion-year lifetimes. By contrast, metal-rich stars formed recently, from gas enriched by countless previous stellar generations. Their high metallicities mark them as products of mature galactic evolution. Plotting these metallicities against stellar ages derived from evolutionary modeling revealed Andromeda's enrichment history. The relationship wasn't smooth and monotonic as might be expected for gradual, continuous star formation. Instead, the data showed stepwise increases, periods of rapid enrichment separated by plateaus. This pattern indicated episodic evolution, eras of intense star formation, and supernova activity that rapidly enriched the interstellar medium, alternating with quiescent periods when star formation nearly ceased. The episodic nature strongly suggested merger-driven evolution, with each burst triggered by a dwarf galaxy bringing fresh gas to fuel star formation. One particularly revealing JWST observation targeted stars in the giant southern stream, the tidal feature mentioned earlier. These stars, ripped from a dwarf galaxy that Andromeda consumed approximately 2 billion years ago, retain the chemical signatures of their origin. Their metallicities averaged half solar, significantly lower than stars in Andromeda's main disk at the same epoch. This discrepancy revealed that dwarf galaxies evolve chemically more slowly than massive systems, their lower star formation rates producing fewer supernovae and slower metal enrichment. When Andromeda cannibalized this dwarf, it incorporated a population of stars chemically distinct from its native population, creating diversity that JWST observations can now detect and map. The implications extend to understanding galactic archaeology. Just as archaeologists excavate sites layer by layer to reveal human history, galactic astronomers dissect stellar populations by age and chemistry to reconstruct galaxy formation. Andromeda's stellar populations, now measurable in unprecedented detail thanks to JWST, preserve a fossil record of formation, growth, and evolution spanning 10 billion years. Each population formed under specific conditions from gas with specific composition, and those formative circumstances left permanent signatures that current observations decode. JWST also detected stars with unusual chemical patterns that hint at exotic formation environments. Some metal-poor stars showed enhanced abundances of elements like strontium and barium, heavy elements formed through the slow neutron capture process in asymptotic giant branch stars. Others exhibited elevated alpha element ratios, signatures of enrichment dominated by massive stars exploding as Type II supernovae rather than the mix of Type Ia and II that dominates modern enrichment. These chemical peculiarities identified stars formed in specific environments, small dwarf galaxies, globular clusters, or the early galactic halo, adding yet more complexity to Andromeda's population structure. The oldest stars JWST detected in Andromeda likely formed within the first billion years after the Big Bang, making them over 12 billion years old. These ancient survivors, now red giants nearing the ends of their nuclear-burning lifetimes, witnessed the entire history of galaxy formation. They condensed from gas clouds when Andromeda was a fragmentary structure, perhaps not yet recognizable as a coherent galaxy. They saw their parent dwarf galaxy merge with others to build Andromeda's early mass. They watched as successive generations of stars formed, evolved, and died around them. And they endured, surviving to an era when their light could be captured by an infrared telescope to 0.5 million light-years away and analyzed to reconstruct the conditions of their birth. Contrast those ancient stars with the youngest populations JWST observed, stars less than 10 million years old, still embedded in or recently emerged from their natal gas clouds. These infants formed from material enriched by billions of previous stellar generations. Their composition reflects 12 billion years of galactic chemical evolution, heavy elements built up atom by atom through countless supernova explosions and stellar winds. They represent the current endpoint of Andromeda's chemical enrichment, though that enrichment continues as more massive stars evolve and explode. The age range from 12 billion years to 10 million years spans a factor of more than 1,000. Contemplating this temporal depth requires adjusting intuition shaped by human timescales. Recorded human history extends perhaps 5,000 years. Modern science spans for centuries. The entire span of human existence as a species covers a few million years at most. Andromeda's stellar populations span intervals thousands of times longer, encompassing eras when Earth didn't exist, when the solar system hadn't formed, when the universe itself was less than a fifth its current age. This temporal scale carries profound implications for the search for life and intelligence. If civilizations arise in Andromeda, they could span billions of years of galactic history. A technological civilization that emerged when Andromeda's oldest surviving stars formed would predate Earth's formation by 7 billion years. The technological and scientific advances achievable across such spans defy imagination. Yet we detect nothing, no evidence of galaxy-spanning engineering, no obviously artificial structures, no signals that break through the cosmic background. The silence persists despite billions of years of potential development time across trillions of stars worth of opportunity. Several explanations exist, none entirely satisfying. Perhaps technological civilizations inevitably destroy themselves or stagnate before achieving detectability across intergalactic distances. Perhaps they transcend physical existence in ways that render them undetectable by conventional astronomy. Perhaps they exist but pursue goals and methods entirely orthogonal to what we imagine, making them invisible to our searches. Or perhaps life is far rarer than the seemingly favorable conditions throughout Andromeda suggest, rising so infrequently that Andromeda hosts no civilizations despite its vast stellar population and billion-year time spans. JWST observations cannot resolve this mystery, but they provide crucial context. By revealing the formation history of Andromeda's stellar populations, the telescope shows when and where conditions favorable for planet formation existed. The ancient, metal-poor populations likely host few planets, formed as they were from gas containing minimal heavy elements needed to build rocky worlds. Middle-aged populations with near-solar metallicity represent prime candidates, similar enough to solar composition that planet formation should proceed much as it did in our system. The youngest populations may not have developed complex planetary systems yet, their planets still forming or newly formed. Estimating from these considerations, perhaps 10 to 20% of Andromeda's trillion stars possess sufficiently high metallicity and sufficient age to host mature planetary systems. That yields 100 to 200 billion candidate systems, a number so large that even extremely pessimistic estimates for life's emergence would predict millions or billions of living worlds. Yet the cosmic silence continues, unbroken by any signal we can recognize. Andromeda and its vastness becomes a monument to questions we cannot yet answer, a trillion-star laboratory conducting experiments in biology and evolution whose results remain inaccessible. The temporal depth that JWST observations reveal transforms understanding in another way. It demonstrates that galaxies aren't merely spatial structures but historical processes. Andromeda didn't spring into existence in its current configuration. It built up gradually through mergers, accretion, and star formation, each are leaving signatures that persist to the present. The galaxy we observe represents a single frame from a 10 billion-year film, interpretable only through recognizing the temporal dimension underlying spatial structure. This historical perspective affects how we understand galactic properties. Andromeda's current star formation rate, approximately 1 solar mass per year, represents a dramatically reduced level compared to its past. Measurements suggest that the galaxy formed stars at rates 10 to 20 times higher when it was a few billion years old, during epochs when gas remained abundant and mergers brought fresh material. The declining star formation rate reflects gas consumption and heating that makes remaining gas increasingly resistant to collapse. Andromeda is aging, its star formation gradually declining toward eventual quiescence. Yet the timescales involved prevent this from being imminent. At current rates, Andromeda retains enough gas to sustain star formation for several billion years more. The impending merger with the Milky Way will disrupt these projections, bringing a burst of triggered star formation as gas clouds collide and compress. After the merger, the combined system will likely experience a final burst of activity before settling into a quiescent elliptical galaxy, its star formation finally exhausted. These future developments lie billions of years ahead, spans of time comparable to Earth's age, yet they're predictable consequences of dynamics currently observable. Understanding Andromeda's temporal depth means recognizing that the galaxy encodes information extending from near the Big Bang to the present, with implications reaching billions of years into the future. JWST's observations access this temporal dimension through chemical archaeology, dating stellar populations and tracing their origins. The resulting picture shows Andromeda as a product of history, shaped by specific events across specific epochs, interpretable through forensic analysis of its current state. Dark architecture. Everything discussed so far, stars, gas, dust, spiral structure, represents only a fraction of Andromeda's mass. The visible and infrared emitting components that JWST observes account for perhaps 15% of the galaxy's total gravitational mass. The remaining 85% consists of dark matter, a substance that neither emits nor absorbs light at any wavelength, detectable only through its gravitational influence on visible matter. Understanding Andromeda's true scale requires confronting this invisible component, the dark architecture that scaffolds the luminous galaxy we observe. Evidence for dark matter in galaxies emerged from rotation curve studies in the 1970s. Vera Rubin and her collaborators measured the orbital velocities of gas clouds and stars at various distances from galactic centers, expecting to find velocities declining with radius according to Keplerian dynamics. Instead, rotation curves stayed flat or even increased at large radii, implying that galaxies contain far more mass than visible matter alone could provide. The simplest explanation proposed an extended halo of dark matter pervading and surrounding the luminous galaxy, providing additional gravity that maintains high orbital velocities at large radii. Andromeda's rotation curve exhibits this same behavior. Measurements extending to radii of 100,000 light-years from the galactic center show orbital velocities remaining around 250 kilometers per second, far higher than visible matter alone could sustain. Modeling the rotation curve requires a dark matter halo containing approximately 1.5 trillion solar masses, making dark matter roughly 10 times more massive than all stars, gas, and dust combined. This halo extends far beyond the visible galaxy, reaching radii of perhaps 500,000 light-years or more, creating a gravitational potential well within which the luminous components are embedded. JWST observations contribute to understanding dark matter distribution through precise mapping of stellar populations. By measuring the positions and velocities of stars at various locations in Andromeda, astronomers can infer the gravitational field these stars experience. That gravitational field rises from all matter present visible and dark, allowing the dark matter distribution to be constrained through careful modeling. The stellar streams in Andromeda's halo proved particularly valuable for this purpose, as their elongated shapes and narrow velocity dispersions make them sensitive probes of the gravitational potential. One revealing analysis used JWST observations of the giant southern stream to constrain Andromeda's dark matter halo shape. Streams follow orbits determined by the galactic gravitational field. If the dark matter halo is perfectly spherical, streams maintain certain configurations. If the halo is flattened or triaxial, streams follow different paths. Comparing observed stream morphology with simulations for various halo geometries revealed that Andromeda's dark matter halo is likely mildly triaxial, neither spherically symmetric nor strongly flattened, with an axis ratio of approximately 0.8. This degree of asphericity matches predictions from cosmological simulations and confirms that dark matter halos possess structure beyond simple spherical symmetry. The nature of dark matter itself remains mysterious despite decades of investigation. We know it must be massive to produce the gravitational effects observed. We know it must be cold, meaning its particles move at non-relativistic velocities to allow the formation of structure on galactic scales. Beyond these basic requirements, dark matter's identity stays uncertain. Leading candidates include weakly interacting massive particles WIMPs, axions, and sterile neutrinos, but direct detection experiments have so far failed to find convincing evidence for any specific particle. Dark matter remains defined by what it does gravitationally rather than what it fundamentally is. JWST cannot detect dark matter directly. No telescope operating at any wavelength can, given dark matter's defining property of not interacting electromagnetically. But the telescope's precise measurements of luminous matter enable increasingly accurate maps of total gravitational mass through dynamical modeling. Comparing luminous and total mass distributions reveals where dark matter concentrates, how its density varies with radius, and how it responds to perturbations from mergers and tidal interactions. Each constraint reduces the parameter space that dark matter models must occupy. One particularly intriguing possibility involves self-interacting dark matter, a scenario where dark matter particles can collide and scatter off each other through forces beyond gravity. Such interactions would affect dark matter distribution in galactic cores, potentially explaining certain observed features that standard cold dark matter models struggle to reproduce. JWST observations of Andromeda's central regions, where stellar densities reach extreme values, provide tests of this scenario. Preliminary analyses suggest that Andromeda's core is consistent with standard cold dark matter predictions, but uncertainties remain large enough that self-interacting models cannot be definitively ruled out. The dark matter halo's extent dwarfs the visible galaxy. While Andromeda's luminous disk measures to 120,000 light-years across, its dark matter halo reaches perhaps 1,000,000 light-years in diameter before blending into the intergalactic medium. This means the Milky Way's dark matter halo, similar in extent, already overlaps significantly with Andromeda's. The two galaxies are not separated by 2.5 million light-years of empty space. They occupy overlapping regions of a larger structure, their dark matter halos already interacting gravitationally even though their luminous components won't collide for another 4 billion years. This realization transforms the concept of galactic boundaries. Where does Andromeda and intergalactic space begin? The question lacks a clear answer. The stellar disk has a relatively sharp outer edge where star formation ceases and stellar density drops precipitously. The stellar halo extends further, fading gradually with increasing radius. The dark matter halo extends further still, its density declining slowly according to profiles predicted by cosmological simulations. At some radius, perhaps 500,000 to 1,000,000 light-years, Andromeda's dark matter density becomes indistinguishable from the cosmic mean density, but this transition occurs gradually over scales comparable to the halo size itself. Understanding this dark architecture matters profoundly for grasping galactic physics. Dark matter provides the gravitational potential well within which visible matter collects and forms stars. Without dark matter, galaxies as we know them couldn't exist. the gas in protogalactic clouds would lack sufficient gravity to overcome thermal pressure and collapse into star-forming disks. The rotation curves of mature galaxies would follow Keplerian decline, making outer regions gravitationally inbound and susceptible to disruption. Spiral structure would be unstable, unable to maintain coherence against perturbations. In a universe without dark matter, galaxy formation would proceed differently if it proceeded at all. Andromeda also serves as a test case for understanding dark matter behavior during galaxy mergers. The numerous dwarf galaxies Andromeda has consumed each brought their own dark matter halos, which merged with Andromeda's halo during the accretion process. Simulations predict that this merger process should produce substructure in the combined halo, overdense regions where dwarf galaxy dark matter concentrated before being tidally disrupted. JWST observations of stellar streams associated with these mergers provide indirect probes of this dark matter substructure, as streams passing through overdense regions experience additional gravitational perturbations that affect their orbits and morphology. Preliminary analyses suggest that Andromeda's dark matter halo contains less substructure than the most detailed simulations predict, a finding that matches similar results for the Milky Way. This missing satellites problem has generated extensive theoretical discussion. Either simulations overpredict substructure due to incomplete physics, or small dark matter halos exist but failed to form stars for reasons not fully understood, rendering them invisible. JWST's ability to detect extremely faint stellar populations will help resolve this tension, either by finding previously overlooked ultra-faint dwarf galaxies or by confirming their absence and forcing due revision of structure formation theory. The interaction between dark matter and baryonic matter, the normal matter of stars and gas, produces additional complications. Baryonic matter can cool by radiating energy, allowing it to collapse into dense structures like galactic disks. Dark matter cannot cool this way, maintaining a more diffuse distribution. But the baryonic matter's gravity affects dark matter distribution, particularly in galactic cores where stellar densities become high. This baryonic feedback modifies dark matter profiles in ways that depend on galaxy formation history, creating additional complexity that observations must disentangle. For observers attempting to grasp Andromeda's true scale, the dark matter component represents perhaps the most challenging element. We cannot see it, cannot photograph it, cannot capture its emission in any wavelength. Yet it constitutes the overwhelming majority of the galaxy's mass, the foundation that supports and shapes everything visible. Acknowledging this invisible architecture means accepting that our most detailed observations capture only a minority component of the total system. Like studying an iceberg by examining the portion above water while inferring the much larger submerged bulk through indirect measurements. This limitation extends to all of astronomy. Every galaxy we observe consists primarily of dark matter. Every galaxy cluster, every large-scale structure, every gravitational interaction involves dark matter as the dominant component. The luminous universe, the stars and gas clouds and radiant phenomena that telescopes detect, represents mere tracer particles revealing the presence and distribution of the dark matter ocean within which they're embedded. JWST provides exquisitely detailed observations of these tracers in Andromeda, but the bulk of the galaxy remains invisible, knowable only through inference. Yet this invisible component profoundly shapes the visible. Without dark matter's gravity, Andromeda's spiral structure would differ or perhaps not exist. The stellar streams tracing ancient mergers would follow different orbits. The galaxy's rotation curve would decline rather than flatten. The upcoming collision with the Milky Way would proceed differently, the two systems' dark matter halos affecting the merger dynamics as much as their stellar components. Understanding Andromeda requires understanding its dark architecture, the unseen scaffolding that organizes and sustains the trillion star system we observe. Current technology cannot reveal dark matter directly, but future observations will continue refining our understanding of its distribution and properties. JWST's contribution lies in mapping luminous tracers with unprecedented precision, constraining dark matter through increasingly accurate dynamical modeling. Each refinement narrows possibilities, bringing us incrementally closer to understanding this mysterious substance that dominates cosmic mass budgets yet remains stubbornly invisible to all forms of day. Wreck detection. Collision destiny. Andromeda is falling toward us. At this moment, the galaxy moves through space at 110 kilometers per second on a trajectory that will bring it into direct collision with the Milky Way in approximately 4.5 billion years. This isn't speculation or distant possibility. The merger is inevitable, written into the orbital dynamics that govern local group evolution. Understanding this collision destiny transforms how we view Andromeda, converting it from a distant object of study into our galaxy's future partner in one of the most dramatic events the universe stages. The realization that Andromeda approaches rather than recedes came from careful measurement of its radial velocity using the Doppler shift of spectral lines. Most distant galaxies show redshifted spectra, their light stretched to longer wavelengths by the universe's expansion carrying them away from us. Andromeda shows blue-shifted spectra, its light compressed to shorter wavelengths because the galaxy is moving toward us. This blue shift indicates a velocity of approximately 110 kilometers per second, a substantial motion that overcomes the local expansion of space. Andromeda falls toward the Milky Way because the two galaxies' mutual gravitational attraction exceeds the weak expansion that operates on the 2.5 million light-year scale separating them. Early observations could determine only the radial velocity component, the motion toward or away from us along our line of sight. The tangential velocity component, motion perpendicular to the line of sight, remained unmeasured because detecting it requires measuring extremely small angular motions of a distant object against background reference frames. Only in the early 2000s, using the Hubble Space Telescope's precise astrometry capabilities combined with data from the Hipparcos satellite, did astronomers measure Andromeda's tangential motion accurately enough to predict the collision trajectory. Those measurements revealed that Andromeda's motion is nearly entirely radial. The galaxy approaches almost directly toward us with minimal tangential component. This means the collision will be nearly head-on rather than a glancing encounter. The two galaxies will interpenetrate completely, their stars, gas clouds, and dark matter halos passing through each other in a complex gravitational dance that will take several billion years to complete. The eventual result, after multiple passages and tidal interactions, will be a single merged galaxy, a massive elliptical system containing all the matter from both progenitors. Simulations of this merger have been run extensively using supercomputers to model the gravitational interactions of billions of particles representing stars and dark matter. The results show a complex, multi-stage process. First approach occurs in about 4 billion years, when the galaxy's outer regions begin to interact gravitationally. Tidal forces stretch both galaxies, pulling out long streamers of stars. The galactic cores pass by each other at high velocity, separated by perhaps 100,000 light-years, not colliding directly on this first passage. After first approach, the two galaxies separate again, their relative velocity decreased by gravitational interaction but still sufficient to carry them apart temporarily. They reach maximum separation a billion years or so later, then fall back together for a second collision. This time they interpenetrate more deeply, the tidal interaction stronger, more stars flung into intergalactic orbits. The dark matter halos, which began to overlap on first approach, merge substantially during this second passage. Gas clouds collide and shock, triggering enormous bursts of star formation that briefly increase the combined system's luminosity substantially. Subsequent passages follow at shorter intervals as energy dissipates through gravitational interactions. Each collision scatters stars into wider orbits, transforming the ordered rotation of disk galaxies into the random motions of elliptical galaxy stars. After perhaps a dozen orbital passages over 3 to 4 billion years, the merger completes. The final system, sometimes called Milkomeda in popular accounts, will be a massive elliptical galaxy containing approximately 2 trillion solar masses of stars plus accompanying dark matter. The beautiful spiral structures of both progenitors will be completely destroyed, their ordered disks replaced by a roughly spheroidal distribution of stars. JWST observations contribute to understanding this future collision by revealing Andromeda's current structure in unprecedented detail. The stellar populations, spiral architecture, and dark matter distribution that the telescope maps all feed into merger simulations, constraining models and improving predictions. Understanding Andromeda's mass distribution, for instance, affects calculated trajectories and merger timescales. If Andromeda proves more massive than previous estimates suggested, gravitational interactions will be stronger and the merger may complete more quickly. If the dark matter halo extends further than expected, tidal interactions will begin at larger separations. One particularly important constraint concerns Andromeda's satellite galaxy population. Andromeda hosts dozens of satellite galaxies, smaller systems bound by gravity to orbit the larger galaxy much as the Magellanic Clouds orbit the Milky Way. During the merger, these satellites will be scattered, some ejected into intergalactic space, others captured by the merged system, still others disrupted completely by tidal forces. JWST observations that detect and characterize these satellites improve models of their fates, helping predict what the local group will look like billions of years after the merger completes. For any hypothetical inhabitants of either galaxy during the merger, the event would be simultaneously dramatic and subtle. Dramatic because the night sky would transform completely over timescales of millions of years. Andromeda, currently a faint smudge in Milky Way skies, would grow progressively larger and brighter as it approached, eventually spanning significant portions of the visible sky. The merger would trigger spectacular bursts of star formation visible as brilliant regions of newly formed stars and glowing gas. Tidal effects might stretch the Milky Way visibly, creating unusual spiral patterns or even disrupting local spiral structure entirely. Yet subtle because individual star collisions would be extraordinarily rare despite the galaxies interpenetrating. Stars are tiny compared to the distances separating them. In galactic collisions, stars pass by each other like snowflakes in colliding snowstorms, countless near misses but very few actual impacts. The Sun and its planets would almost certainly survive the merger intact, merely scattered into a new orbit around the merged system's center. The main danger would come not from stellar collisions but from gravitational perturbations that might alter planetary orbits or send comets plunging toward the inner solar system. Of course, these considerations remain academic given that the collision lies for 0.5 billion years in the future. The Sun will have evolved significantly by then, expanding into a red giant that renders Earth uninhabitable. If humanity or its descendants still exist, they will presumably have dispersed beyond the solar system long before the merger begins. The collision poses no threat to present-day Earth but serves as a reminder that even galaxies, despite their vast scales, participate in dynamic interactions and evolution. The merger also provides context for understanding Andromeda's past. The stellar streams and population complexities that JWST observations revealed testify to previous mergers with smaller galaxies. The collision with the Milky Way represents the culmination of this pattern, a merger between near equals rather than the consumption of small satellites. After Milkomeda forms, it will likely undergo no further major mergers. The local group contains no other galaxies comparable in mass to the Milky Way or Andromeda. The merged system will be the dominant gravitational structure for tens of millions of light years, accreting only the occasional dwarf galaxy and gradually aging as star formation depletes remaining gas. This fate merger into an elliptical galaxy followed by gradual decline represents the typical end state for galaxies in group environments. Galaxy clusters, containing hundreds or thousands of galaxies in relatively small volumes, experience frequent mergers that produce massive ellipticals. Isolated galaxies evolve more peacefully, maintaining spiral structures for longer periods. Group environments like the local group occupy an intermediate regime, with occasional mergers between the most massive members creating ellipticals while smaller galaxies persist as satellites. Understanding the collision also illuminates why JWST observations of Andromeda matter beyond immediate scientific returns. We're documenting the structure and properties of a galaxy that will soon, on cosmic timescales, cease to exist as an independent system. Future astronomers residing in Milkomeda will never see Andromeda as we see it now, a separate spiral galaxy approaching across intergalactic space. They'll reconstruct its properties through stellar archaeology, much as we reconstruct the properties of dwarf galaxies that Andromeda has already consumed. Our current observations become historical records, documentation of a galactic configuration that the merger will permanently erase. This temporal perspective adds poignancy to viewing Andromeda. The photons JWST detects left Andromeda to 0.5 million years ago, carrying information about the galaxy as it appeared in that epoch. But that Andromeda continues to evolve, forming new stars, accreting gas, orbiting in the local group's gravitational field. By the time we observe it, the specific star-forming regions we see have already evolved significantly. The stellar streams have shifted position. The spiral arms have rotated through significant angles. We observe not current Andromeda but historical Andromeda, forever seeing it as it was, never as it is. Yet this limitation affects all astronomical observation. Light travels at finite speed, so we observe the distant universe progressively further into the past. Andromeda's 2.5 million year light travel time is negligible compared to the billions of years that light from distant galaxies requires to reach us, but the principle remains the same. All astronomy is archaeology, studying evidence from earlier epochs to reconstruct history and understand processes. For Andromeda, this archaeological perspective combines with knowledge of its impending merger to create a complete narrative arc. Past revealed through stellar populations, present observed through telescopes, future predicted through orbital dynamics. The collision destiny transforms Andromeda from mere object to participant in a shared story. The galaxy ceases to be simply an external system worthy of study and becomes our future partner, a component of our cosmic context as important as the Milky Way itself. Understanding Andromeda means understanding our galactic future, preparing intellectually for transformations that will reshape the local group fundamentally. JWST's observations document the prelude to this transformation, capturing Andromeda in its current pristine spiral state before the merger begins. Living architecture. 1 trillion stars create 1 trillion opportunities for planets, and planets create opportunities for life. This chain of possibility transforms Andromeda from a collection of nuclear furnaces into a potential biological laboratory operating on scales that dwarf any earthly comparison. If the laws of biochemistry apply universally, the life emerges wherever conditions permit. Then, Andromeda should host an abundance of living worlds that makes Earth's solitary example seem statistical. Why insignificant? Yet we detect no evidence of this hypothetical Andromedan biosphere, no signatures that separate biological worlds from sterile ones across 2.5 million light-years of distance. The question of life in Andromeda operates at the intersection of astrophysics and biology. Astrophysics tells us about stellar populations, chemical compositions, planetary system formation. Biology tells us about the requirements for life as we understand it: liquid water, organic chemistry, energy sources, stable environments persisting for evolutionary timescales. Combining these domains produces estimates necessarily uncertain about how many worlds in Andromeda might host life, from simple microbes to complex ecosystems to technological civilizations. Start with planets. Current understanding suggests that planet formation occurs commonly around stars, perhaps nearly universally. Observations of protoplanetary disks in the Milky Way show that circumstellar disks of gas and dust are standard features of star formation. These disks provide the material from which planets condense. While early theories suggested planet formation might be rare and special, recent exoplanet discoveries indicate that most stars host planetary systems. If this applies to Andromeda, then the galaxy contains perhaps 800 billion to 1 trillion planetary systems, averaging 1 or more planets per star. Not all these planets would be candidates for life. Gas giants lack solid surfaces and possess atmospheric conditions hostile to biochemistry as we understand it. Planets orbiting too close to their stars experience extreme temperatures and radiation. Planets too distant freeze solid, their surfaces coated with exotic ices. The habitable zone, the range of orbital distances where liquid water can exist on a planet's surface, occupies a narrow shell around each star, wider for luminous stars, narrower for dim ones. Estimates suggest perhaps 10 to 20% of planetary systems might include a rocky planet within this habitable zone. This yields roughly 100 to 200 billion potentially habitable worlds in Andromeda, an extraordinary number that seems to guarantee abundant life. But habitability doesn't ensure habitation. A planet might orbit at the right distance yet lack water, possess a toxic atmosphere, experience violent climate instability, or suffer frequent sterilizing impacts from asteroids or comets. The fraction of habitable worlds actually inhabited remains perhaps the key unknown in astrobiology. Conservative estimates place it below 1%. Optimistic scenarios suggest it might exceed 50%. The true value determines whether Andromeda hosts billions of living worlds or millions, or merely thousands. JWST cannot detect individual planets in Andromeda directly. At 2.5 million light-years distance, even the galaxy's brightest stars appear as mere point sources. The angular separation between a star and its planets, measured in milliseconds at best, lies far beyond the telescope's resolving power. What JWST can do is characterize stellar populations by age and metallicity, establishing which stars are likely to host planets and which form from gas to metal pour to build substantial rocky worlds. This statistical approach constrains the number of potential habitats even if individual systems remain undetectable. The oldest, most metal-poor stellar populations in Andromeda formed over 10 billion years ago from nearly pristine primordial gas, likely host few if any rocky planets. Heavy elements like silicon, iron, and oxygen are required to build terrestrial worlds, and these elements existed in very small quantities when those ancient stars formed. By contrast, middle-aged stars with near-solar metallicity, formed 5 to 8 billion years ago, represent ideal candidates. They possess sufficient heavy elements for planet building, and they've existed long enough for any biospheres to develop complexity. The youngest stars, less than 1 billion years old, have the highest metallicities but may not have granted sufficient time for life to evolve beyond primitive stages. Though this depends strongly on how quickly life can arise and complexify. Focusing on optimal populations middle-aged, metal-rich stars, the candidate pool might narrow to 50 to 100 billion systems. If 1% hosts life, that yields 500 million to 1 billion living worlds. If 10% hosts life, we reach 5 to 10 billion biospheres. These numbers dwarf Earth's singular example, suggesting that life in Andromeda, if it exists at all, exists abundantly rather than as rare isolated instances. The galaxy becomes a biological experiment repeated billions of times with varying initial conditions and natural survey of biochemistry's possibilities. Yet none of this hypothetical abundance manifests in observations. Astronomers have searched for technosignatures, evidence of technological civilizations in various forms. Radio signals of the type Earth has been broadcasting for a century would be detectable if sufficiently powerful and directed toward us. Infrared excess from massive astroengineering projects that harness stellar energy output would appear in galaxy-wide observations. Atmospheric biosignatures like oxygen and methane in disequilibrium, detectable through spectroscopy, might reveal biological activity. None of these searches have yielded convincing positive results for Andromeda or indeed for any galaxy. The absence demands explanation. Perhaps life is far rarer than the optimistic estimates suggest, arising only under highly specific conditions that Earth happened to satisfy but that most potentially habitable worlds lack. This rare Earth hypothesis points to factors beyond simple habitability: plate tectonics to regulate climate, a large moon to stabilize rotational axis, a massive outer planet to deflect comets, just the right amount of water to create land-ocean balance. If life requires this specific combination, occurrence rates might be far below 1%, making even Andromeda's trillion stars insufficient to guarantee abundant biospheres. Alternatively, perhaps life rises readily but rarely advances beyond microbial stages. Earth remained a microbial planet for roughly 3 billion years before complex multicellular life emerged. If this trajectory is typical, then most living worlds host only microbes, too simple to generate detectable atmospheric biosignatures or technological civilizations. The galaxy might be teeming with bacterial biospheres that leave no signatures detectable across intergalactic distances, creating the illusion of lifelessness despite widespread biology. A third possibility suggests that technological civilizations arise but inevitably fail before achieving galaxy-spanning detectability. They might destroy themselves through warfare, environmental collapse, or technological accident. They might stagnate culturally or technologically, never developing the motivation or capability for astroengineering or interstellar communication. They might exist for geologically brief periods, thousands or millions of years, too short a window for detectable signals to propagate across galactic distances during the brief window when other civilizations exist to detect them. Or perhaps our assumptions about detectability are simply wrong. An advanced civilization might employ communication technologies that appear to us as natural phenomena, or might deliberately avoid broadcasting detectable signals, or might have progressed beyond physical existence in ways that render them undetectable by conventional astronomy. What seems like absence might reflect our observational limitations and imagination failures rather than actual lifelessness. Andromeda might host a rich ecosystem of intelligences operating outside our detection paradigms, invisible not through absence but through our inability to recognize their presence. JWST's observations of Andromeda don't resolve these questions but provide crucial context. By mapping stellar populations and characterizing their properties, the telescope establishes the stage on which any Andromedan biology must perform. The detection of organic molecules in the interstellar medium demonstrates that chemical precursors to life exist throughout the galaxy. The identification of older stellar populations with sufficient metallicity shows that suitable planetary systems have existed for billions of years, granting ample time for evolution. The revelation of the galaxy's true scale emphasizes the magnitude of the question. We're not asking whether a handful of stars might host life, but whether trillions of potential habitats produce biology. The cosmic silence, maintained despite these favorable conditions, becomes more puzzling with each observation that confirms Andromeda's suitability for life. Either we fundamentally misunderstand biology's requirements or prevalence, or we're missing something crucial about detection methods or civilization behavior. The question extends beyond Andromeda to the universe at large. JWST observes thousands of galaxies, all apparently devoid of obvious technosignatures, but Andromeda provides the clearest example. The nearest galactic system where detailed observations can test specific hypotheses. For humans contemplating our cosmic context, the possibility of life in Andromeda carries profound implications. If the galaxy hosts abundant biospheres, then life is a cosmic commonplace, rising reliably wherever conditions permit. Life becomes typical rather than special, our biochemistry and evolution representative of processes occurring throughout the universe. Discovering this would place humanity within a vast biological context, part of a galaxy-spanning community of living worlds, even if they remain forever inaccessible across intergalactic distances. Conversely, if Andromeda proves lifeless despite its trillion stars and billions of years, then life is extraordinarily rare, requiring conditions so specific that even vast stellar populations might not satisfy them. Life becomes precious beyond measure, possibly the only living world in the local group, perhaps one of a tiny handful in the entire observable universe. This scenario places enormous responsibility on humanity as potentially the sole bearers of biology and consciousness in our cosmic neighborhood. The only means by which the universe becomes aware of itself within a volume encompassing dozens of galaxies. We cannot yet determine which scenario applies. JWST lacks the capability to detect biosignatures on distant exoplanets in Andromeda. Even for nearby stars in our own galaxy, such detection pushes current technology. Future observatories might achieve such detection, searching for atmospheric disequilibrium or other signs of biological activity. But for now, Andromeda's potential biospheres remain speculative, grounded in reasonable extrapolation from terrestrial biochemistry, but unconfirmed by empirical evidence. The galaxy thus becomes a mirror for our uncertainties about life's prevalence and nature. Its trillion stars represent opportunity at unimaginable scale. Its silence represents mystery that observations have yet to penetrate. JWST reveals the stage, the stars, the chemistry, the environments, but not yet the actors. The living architecture remains potential rather than confirmed, a possibility that transforms how we view the galaxy while remaining frustratingly beyond current detection capabilities. We see the home but cannot determine if it's inhabited. Collision physics. When Andromeda and the Milky Way collide, The event will unfold according to physical laws that operate with indifference to human categories or concerns. Gravity will dominate, pulling the two systems together along trajectories determined by their masses and velocities. Stars will follow ballistic paths through regions where gravitational fields fluctuate wildly as the two galaxies interpenetrate. Gas clouds will collide and shock, converting ordered motion into heat and turbulence. Dark matter halos will pass through each other almost unimpeded, their particles interacting only gravitationally. Understanding this collision requires examining the distinct behaviors of the galaxy's various components under extreme gravitational conditions. Stars behave as collisionless particles during galactic mergers. Despite there being hundreds of billions of stars in each galaxy, the vast distances separating the mean individual collisions are extraordinarily improbable. Calculate the probability. A typical star has a diameter of about 1,000,000 kilometers. Stars in the galactic disk are separated by light years, distances of trillions of kilometers. The ratio of stellar size to separation is roughly 1 to 10 million. During a galactic merger, stars pass through the opposing galaxy much like grains of sand passing through a distant cloud of similar grains, countless close approaches but essentially zero actual impacts. This collisionless behavior means stars respond only to the overall gravitational field created by the combined mass distributions of both galaxies. As Andromeda approaches, its gravitational field begins to perturb Milky Way stars, altering their orbits subtly. During the first close passage, these perturbations intensify. Stars in the outer regions of both galaxies experience differential gravitational forces, tidal forces that pull them away from their parent systems. Long tidal tails form, streams of stars stretching hundreds of thousands of light years into intergalactic space, dramatic structures that simulations reproduce in stunning detail. The galactic cores behave differently. Each galaxy's central supermassive black hole, weighing hundreds of millions of solar masses, creates a deep gravitational potential well. During the merger, these black holes follow complex orbits determined by dynamical friction, a process where gravitational interactions with surrounding stars progressively slow the black holes and draw them toward the system's center of mass. Eventually, after several billion years and multiple galactic passages, the two black holes sink to the merged system's core where they orbit each other progressively closer until finally merging in a cataclysmic event that releases gravitational waves of staggering amplitude. This black hole merger represents one of the most energetic events the universe produces, exceeded only by the Big Bang itself. When two supermassive black holes weighing roughly 100 million solar masses each spiral together and merge, they release energy equivalent to several percent of their combined mass entirely converted to gravitational waves according to Einstein's E equals mc. For comparison, stellar nuclear fusion converts about 0.7% of mass to energy. The black hole merger is several times more efficient, though all the energy emerges as gravitational waves rather than electromagnetic radiation, making it invisible to optical or infrared telescopes like JWST. Gas dynamics during the collision differ dramatically from stellar behavior. Unlike stars, gas clouds can and do collide, their constituent atoms interacting electromagnetically. When two gas clouds moving at several hundred kilometers per second encounter each other, the collision creates shock waves. The kinetic energy of ordered motion converts to heat, raising gas temperatures to millions of degrees. This shock gas radiates X-rays, creating spectacular high-energy displays that space-based X-ray telescopes can detect in nearby merging galaxies. The collision also compresses gas to higher densities, triggering massive bursts of star formation. These starburst episodes represent the most intense star formation events the universe produces. In merging galaxies observed at earlier cosmic epochs, star formation rates can reach hundreds or even thousands of solar masses per year, compared to the Milky Way's current rate of about 1 solar mass per year. The physical mechanism driving such extreme rates is straightforward. Colliding gas clouds create high-pressure regions where gravity can overcome thermal pressure, allowing cloud collapse and star formation to proceed rapidly. The result is the formation of millions of new stars over timescales of tens of millions of years, a brief but spectacular burst. The newly formed stars in these starbursts are predominantly massive. The compressed, High-density conditions favor formation of stars significantly more massive than the Sun, stars that live fast, shine bright, and die young. These massive stars dominate the optical and ultraviolet light output of the merger, creating the brilliant blue colors characteristic of starburst galaxies. But they also evolve quickly, exhausting their nuclear fuel in millions of years and exploding as supernovae. The combined effect of many closely spaced supernovae can drive powerful galactic winds, blowing gas out of the galaxy entirely and potentially suppressing star formation in later epochs. Dark matter, which dominates both galaxies' mass budgets, participates in the merger but in peculiar ways. Dark matter particles interact only gravitationally, passing through both ordinary matter and each other without colliding, assuming standard cold dark matter properties. During the first galactic passage, the dark matter halos interpenetrate almost completely. But unlike the luminous components, which can dissipate energy through various processes, dark matter remains essentially collisionless and dissipationless. The dark matter halos pass through each other, emerge on the other side, and then fall back together for subsequent passages. This behavior means dark matter mergers complete somewhat differently than stellar mergers. While stars can be scattered into wide orbits through gravitational interactions, losing orbital energy and settling toward a merged configuration, dark matter maintains more of its initial orbital energy. The final dark matter distribution in the merged system therefore tends to be slightly more extended than the stellar distribution, though both eventually reach equilibrium configurations determined by the total mass and angular momentum of the system. Simulations of the Andromeda Milky Way collision incorporate all these components, running calculations that track billions of particles representing stars, dark matter, and gas clouds. The computational challenge is immense. Gravitational interactions between particles scale as the number of particles squared, making direct n-body calculations prohibitively expensive for realistic particle numbers. Modern simulations employ various approximations and algorithms to make the problem tractable, typically representing each galaxy with tens of millions to billions of particles and evolving the system forward in time steps small enough to capture the dynamical evolution accurately. Results from these simulations show remarkable consistency across different research groups and methods. The basic evolutionary sequence: first passage, separation; second passage, eventual merger into an elliptical galaxy, remains robust across different initial conditions within reasonable ranges. Specific details vary: the exact timing of each passage, the morphology of tidal tails, the efficiency of star formation, the fate of satellite galaxies. But the overall picture stays stable, lending confidence that our understanding of merger physics, at least at this coarse level, captures essential reality. One simulation detail deserves special attention: the fate of the solar system during the merger. Current models suggest that the Sun, located roughly 26,000 light-years from the Milky Way's center in a fairly typical disk orbit, will likely be scattered into a more extended orbit during the merger. Instead of residing in a disk 50,000 light-years from the center, the solar system might end up 100,000 or even 200,000 light-years from the merged galaxy's core. This scattering is essentially random. Other stars from similar initial locations might end up closer to the core or be flung into intergalactic space entirely. The probability of the Sun experiencing a close encounter with another star during this process remains vanishingly small despite the violent dynamics. Even during the most chaotic phases of the merger, when stellar densities peak as the two galactic cores pass through each other, the volume of space vastly exceeds the volume occupied by stars themselves. For the solar system specifically, the main risk comes not from stellar collisions but from gravitational perturbations that might disturb the Oort cloud, the distant reservoir of comets orbiting the Sun at distances of tens of thousands of astronomical units. Perturbations could send showers of comets falling toward the inner solar system, increasing impact rates on Earth and other planets for periods of millions of years. But this remains academic given the merger's timescale. The collision begins approximately 4.5 billion years from now. The Sun will have evolved into a red giant by then, expanding to engulf Mercury and Venus and rendering Earth a lifeless cinder. The detailed fate of individual planets during the merger becomes irrelevant when those planets will already be sterilized or destroyed by solar evolution. The merger poses no threat to Earth's biosphere because Earth's biosphere will already have ended through stellar rather than galactic processes. For hypothetical observers residing in artificial habitats or on worlds orbiting longer-lived stars, the merger would provide spectacular viewing. The night sky would transform over millions of years as Andromeda grew from a small fuzzy patch to a vast structure dominating the celestial sphere. Tidal tails of stars would stream across the sky in dramatic arcs. Regions of intense star formation would glow brilliantly, creating new constellations of bright blue stars. The galactic plane, currently a faint band of light called the Milky Way, would be disrupted and eventually dissolve entirely as the disk's ordered structure randomized into the spheroidal distribution. Characteristic of elliptical galaxies. Understanding collision physics provides context for JWST observations of Andromeda, the galaxy's current structure, spiral arms and stellar populations, and dark matter distribution. Represents initial conditions for the upcoming merger. Everything JWST observes: the mass, concentrations, the rotation curve. The stellar demographics feeds into simulations predicting merger evolution, and proved observations lead to refined predictions, reducing uncertainties about specific outcomes even as the general picture remains stable. The collision also contextualizes galactic evolution broadly. Most galaxies in the universe have experienced mergers at some point in their histories. The largest elliptical galaxies in rich clusters grew through dozens or hundreds of mergers over cosmic time. Even spiral galaxies like the Milky Way and Andromeda show evidence of past mergers with smaller systems. The upcoming Andromeda-Milky Way collision represents a relatively late example of a process that has shaped galactic populations throughout cosmic history, one final major merger before the local group's dominant galaxy settles into long-term evolution as an elliptical system.